So before I dive into the question of how we compare our models to observations, let me briefly remind you of the basic working principle of core collapse supernova explosions, or neutrino-driven core collapse supernova explosions. So the basic picture looks like that. A few hundred milliseconds after the collapse of the iron core, a shock front has formed, which stagnates deep inside of the collapsing star at typical radii of 100 to 200 kilometers. And during the collapse of the iron core, a huge amount of gravitational binding energy is released, several times 10 to the 53 ergs. And this gravitational binding energy is initially stored in a puffed up protoneutron star, which is depicted in the center. And this protoneutron star cools and contracts over timescales of roughly 10 seconds. Most of the neutrino emission that is produced is escaping from the star more or less unhinderedly, but a small fraction of less than 1% is reabsorbed in the surrounding layers around the protoneutron star, which can trigger a successful runaway shock expansion with actually the aid of hydrodynamic instabilities. So what's the status of the field until recently? So with the first computer simulation, it has soon become clear that core collapse supernovae are intrinsically multidimensional phenomena. So they need to be modeled in 3D. And also neutrino physics is important. So one needs neutrino radiative transfer calculations in 3D, which is quite computationally challenging. So, but there's a growing number of groups which have nowadays successful shock revival in self-consistent explosion models. However, one of the major shortcomings is that most of these models have only been carried out for timescales of roughly a second or so because of the high computational costs, with a few exceptions. But a timescale of 1 second is way too short to explain the explosion properties of observed supernovae. So this leaves us with a question about explosion energies, nickel yields, and kick velocities, so how they can be explained. That was the main goal of my project, namely to continue a set of successful explosion models which have been simulated with detailed neutrino transport for about 1 second, taking over those models and continuing then for timescales of 10 seconds with a somewhat more approximate treatment of the neutrino physics, which allowed us to simulate the models in full 3D for such long timescales, which are necessary to yield convergence of the properties. So this table is a bit crowded, but don't worry about the details. It just shows you our set of models which we simulated. In total, we have 14 3D models. 8 of them are successful explosion models, which are carried out for timescales of roughly 10 seconds. And we also have 6 black hole forming models in our model suite, which are simulated until the time of black hole formation, which occurs on timescales of less than a second for the considered models. So let's first have a look at the progenitor structures of some of those models. So here in those plots, you can see the densities and the specific entropy as a function of enclosed mass. And most notably, the low mass progenitors have steeply falling density profiles at the edges of their iron cores. Whereas more massive progenitors, here around 20 solar masses, have more shallow density profiles outside of the iron core. Why is this important? Because the density profile or density structure determines the mass accretion rate onto the central object during the explosion phase. So here you can see an overview of some of the characteristic explosion properties during the first half second, showing on the left upper panel the mass accretion rate measured at 400 kilometers, upper right the shock radius, lower right the neutron star, and lower left the neutron star mass, and lower right the neutron star radius as a function of time after core bounce. As I mentioned in my previous slide, the low mass models have rather steeply declining density profiles, which leads to a sudden or quick drop of the mass accretion rate onto the central object. Consequently, the neutron stars formed in those explosions are rather low, and the explosions are triggered rather promptly and easily. Actually, these models do even explode in 1D. Here, I show you how this looks like when plotting cross-sectional cuts of the radial velocity. So just focus on the top row. You can see that both of our considered low mass models, a 9 and a 9.6 solar mass model, explode rather spherically symmetric overall. However, in case of more massive progenitors, the mass accretion rate remains at rather high values even after several hundred milliseconds after the core bounce. This leads to, first of all, higher neutron star masses, but also a more delayed onset of runaway shock expansion. This gives the models enough time to grow a significant amount of non-radial hydrodynamical instabilities. And as you can see here in those snapshots of two of our models, those explosions develop in a highly aspherical manner. And notably, until very late times, until several seconds after the core bounds, there are accretion flows reaching close to the central protoneutron star for several seconds. And this is one important ingredient for explaining the growth of the explosion energy towards the observed values of around 1 beta. And this I want to show you here. So I show you now explosion energies, so the energy that is stored in the expanding supernova ejecta as a function of time. And that's the point where most 3D models have been until recently. So they have been simulated until less than a second. And at those times, the explosion energy only starts to rise slowly. But so actually, as you can see here, the explosion energies of our models only grow over timescales of several seconds. Why? Because of the mentioned accretion downflows, which reach close to the central protoneutron star, where they can gain energy by neutrino heating, then being re-ejected. And the explosion energies only level off after several seconds. And we find that the low mass explosions have energies of less than 0.1 beta, whereas the more massive models reach explosion energies in excess of the canonical 1 beta. So in very good agreement with the values observed from observations. Yeah, in the lack of time, I don't want to talk about the nucleosynthesis yields, but if you're interested, there's a paper out which appeared on the APJ letters in collaboration with Andres Sieverding, focusing on the detailed nucleosynthesis of one of our models. And maybe one key point here is that in our 3D models, we find quite an enhanced production of titanium-44 compared to 1D models, which is a quite important key takeaway point here. But during the rest of my talk, I want to focus on neutron star and black hole recoil kicks. So Rio, in his talk yesterday, just talked about rocket kicks over long timescales. Now I'm talking about birth kicks on timescales of a few seconds. So actually, those results have been published in a paper which appeared on the arXiv just a bit more than 1 week ago. So please check this paper out if you're interested in the details. So, and there are two basic mechanisms for explaining high spatial kick velocities of neutron stars. First one is asymmetric emission of neutrinos, and the second one is the asymmetric ejection of ejecta gas. And both of these mechanisms are in play in our 3D core collapse supernova models. So you can see the low mass models, they yield quite low neutron star kicks of only 100 to 200 kilometers per second, which are mainly coming from neutrino-induced kicks. Whereas for the higher mass models, the kicks are dominated by hydrodynamical effects, mainly by asymmetric ejecta gas. So the explosion energy roughly scale, the neutron star kick velocities roughly scale with the explosion energy, but that's not the full story. So actually, the explosions also need to be highly asymmetric, which can be seen when you compare the two blue curves. So it's basically two similar models with slightly different explosion energy. So the dark blue curve is a more energetic explosion, but it has a lower kick velocity. And why is that the case? Because the less energetic model is way more asymmetric, as you can see here if you compare the cross-sectional cuts of those two models at late time. So the upper model shows a very strong dipolar deformation, whereas the lower model is more spherically symmetric. So for getting a high neutron star recoil kick, you need both a lot of momentum in the expanding ejecta gas, which corresponds to high explosion energies, but also very strong asymmetries in the explosion. So yeah, this just summarizes our results of the hydrodynamic kicks. For low mass explosions, we find quite little or quite small hydro kicks because the ejecta are more or less spherically symmetric and the explosion energies are low. But for high mass models, we find hydrodynamical neutron star kicks of several hundred kilometers per second, in some extreme cases, even more than 1,000 kilometers per second. For all models, we get neutrino-induced kicks on the order of 100 to 200 kilometers per second, which, as I said, are the dominant kick mechanism for low mass stars. For high mass stars, as I said, the hydrodynamic kicks are dominant over the neutrino-induced kicks. For the black hole models we simulated, we find purely neutrino-induced kicks of only a few kilometers per second, but those are models which form black holes via complete collapse. So there is no asymmetric mass ejection. So the only kick mechanism for those cases is asymmetric neutrino emission. So this is my last slide, which summarizes our main results for neutron star and black hole kicks. So on the left part, you can see the outcomes for neutron star. On the right-hand side, the outcome for black hole kicks. Orange symbols denote the contribution from neutrino-induced recoils. Blue symbols are the hydro kicks, and black are the total kicks. And as I said, at the low mass end, the neutrino kicks are purely neutrino-induced, whereas for higher mass models, the kicks are strongly determined by hydrodynamical effects. And interestingly, our outcomes for black hole kicks are in very well agreement with the with the single line spectroscopic binary, which has been presented by Tomer yesterday. So this is quite nice confirmation that some of the black holes receive kicks probably only by asymmetric neutrino emission without any mass ejection. With that, I'm at the end. I leave you with my summary slides, and I thank you for your attention, and I'm happy to take questions. Thank you, Alok.
Hi. Yeah. Could you please explain again what you mean by explosion energies? Is it the flux of energy, or is it the?
It's the energy that is contained in the expanding ejector. So basically, it's kinetic plus internal minus gravitational energy of the unbound post-shock ejector.
So how come in this plot, why is it not monotonic when you go further to late time? Like when I'm thinking about the quantity you were mentioning, I imagine it should just sort of be monotonic with time, right? Or
I mean, there are two effects. So basically, the neutrino energy, the explosion energies can only grow as long as there is new energy pumped into the ejector. And this is, as I explained, but happening in accretion flows that come close to the central object where the neutrino energy is absorbed. At late time, so after a few seconds, the neutrino luminosity from the central object declines drastically. So basically, there's no strong neutrino heating at late times. And also at late times, the densities around the central objects are declining. So basically, it's when the explosion is on its way, everything is just expanding and you thus level off.